Hello, grade 11 university and grade 12 college physics students. This is Mr. Musklow again. And like yesterday, I have a video for today's lesson. So here's how today is going to run. I have a video lesson on alternating current that you are all going to watch. And then whenever you've finished watching the video, you can spend some time working on the textbook questions for this section. Now, when you finish the textbook questions, you can then start going through the concept check questions, because I'll remind everyone that you do have your electricity and magnetism test on Tuesday. And so this is kind of our concept check day as well. Yeah, and so I was just thinking what would make the most sense would be for you to just go through the concept check questions on your own for today. I do plan on being back on Monday unless things change. So the plan right now then would be for me to take up the concept check questions on Monday. I'll just see if anyone has any questions about the concept check questions on Monday so that we can address any confusions about the concept check then. And then, like I said, the test itself is going to be on Tuesday. And I've mentioned before that you're definitely going to get the full period on Wednesday to work on your culminating. Okay, so you certainly have lots to do. After this video lesson, you have textbook questions and then a concept check, and you also have a culminating that you can work on. So everybody definitely has something to do today. There's no way that students have no work to do today. Okay, so with that, we'll get started with today's lesson, which is on alternating current. Now, alternating current is exactly what it sounds like just from the name. An alternating current is a current that changes direction. So up until this point in the unit, we've only really ever thought about direct current, which is a type of current that's only flowing in one direction around a circuit. But alternating current, we're going to see, is different. The current instead is switching directions back and forth and back and forth. And it might not be clear right now how that works exactly or why the electricity in our homes is an alternating current, but that's basically what today's lesson is all about. And we're also going to learn a little bit about household circuits. So, like how things are actually wired in your home. And so I quite like this stuff. I think it's kind of interesting. It gives you an opportunity to learn a bit about, how electricity is actually wired in the real world, and might answer some questions that you've wondered before about certain things. All right. Oh, and I forgot to mention, you'll notice that I didn't provide any handout for this PowerPoint. There is a reason. The reason being basically is that I don't think it would be particularly useful for you to have a printout of the PowerPoint slides for this. There's actually, I think, how many? 18 slides in total, and I think essentially all of them are just pictures. So you'll find that in today's lesson, I'm going to be explaining a lot of things just through the use of images. So I don't really think that would be super useful for students to have, like, pages and pages of just pictures that I'm using to explain things. So it was part of the plan for you to not have a handout for this. Now, this slide asks, why are homes powered by an alternating current? So I just mentioned an alternating current is a current that's switching directions back and forth and back and forth. That might seem kind of strange. Why is the current that is powering our homes an alternating current? And to answer that question, I'm just going to pull up the PhET simulation that we saw yesterday on electromagnetic induction. And this might provide some motivation for why we have alternating current in our homes. All right, so this should look familiar. This was part of yesterday's stuff. Just actually exit that tab. We learned yesterday from yesterday's video that if I want to induce a current in this coil, there needs to be a changing magnetic field near the coil. And so if I actually just check off our field lines here, I'll just turn off the sound. You'll see again that nothing is taking place here if the magnet is just sitting still. So I made clear yesterday that it's not simply a magnetic field that induces a current in this coil. It's a changing magnetic field. And so certainly I can induce a current in this coil while moving the magnet like this. But as soon as I stop moving it, there's no more current induced, and so our light bulb is no longer lit anymore. And so the question is, how can I continually light this light bulb? Because clearly if you're wanting to light your light bulb, you don't just want a flash of light like you get when you just move this magnet like this. You want it to be continually lit. And so how could you do it with this type of setup? Well, you would do it basically just by wiggling this magnet back and forth and back and forth and back and forth. And whenever I do that, when I wiggle this magnet back and forth and back and forth, I'm inducing a current in this coil that's going back and forth and back and forth and back and forth. And so, in fact, whenever I was wiggling this magnet back and forth like this, it was actually an alternating current that I induced in the coil. Now, I am not sure if we're going to have time with our limited time left in the course to talk about electricity generation, which is another interesting topic. That lesson would address how electricity is actually generated, like how electricity generation stations work. I'll just tell you for now that it does not involve just taking magnets and plunging them into coils, wiggling them back and forth. That's not how electricity is generated. But in all seriousness, it's based on the same principle. It's the same idea. And so that's basically why the current in your home is an alternating current. It's because you need a changing magnetic field for a current to be induced. And so to have a setup in which the magnetic field is continually changing, it basically involves inducing a current that switches direction, going back and forth and back and forth. Okay, so that's just some context as to why the current in your home is an alternating current. Now, I'm sure that you have some questions about how this actually works in practice. I'll start out just by showing you a graph of what an alternating current looks like. And so you'll see that we have a graph showing the voltage in the wiring in our homes, as well as the current that's flowing through the wiring. And so the current you'll see is going back and forth and back and forth. It's here at a peak in one particular direction, and then here it's at a trough in the other direction. So back and forth and back and forth like this. Now you'll also see that the voltage is also plotted on this slide, and it matches with the shape of the current. And if you think about what we've been learning so far, this should make some sense, because we see basically that whenever you increase the voltage, the current increases as well. And that's consistent with Ohm's law. Ohm's law tells us that if you increase the voltage across something, the current flowing through it increases. And so, yeah, if you increase the voltage, that's going to increase the current. And that's why we see that these two graphs match each other. And you'll also notice that the current is actually switching direction pretty rapidly here. So it goes through a cycle in 1/60th of a second in Canada. So this is a standard for the electricity in homes in Canada that the frequency is 60 hertz. It's not a worldwide standard. A lot of countries have 50 hertz instead, but in Canada it's 60. And so this means basically that the current is switching direction, going back and forth, but it's doing it very, very rapidly. So I'm going to return to that idea in a minute. Let's see what this actually looks like whenever you have an alternating current flowing through a light bulb. So I have an image of another PhET simulation. Just open our other tab here. And so in this PhET simulation, we have, I'm just trying to collapse this. There we go. Instead of having a direct current source, like you would get from a battery, for example, we instead have an alternating current source. And that's often denoted just with a wiggly line. Okay, the wiggly line you can imagine is showing the voltage like we saw on the slide earlier. So we have our alternating current source. Just going to close the switch. And that's what our circuit looks like with the electrons flowing through the light bulb. And so you'll see, like I had explained earlier, that the current is switching directions, going back and forth and back and forth. The reason more why I wanted to show this to you, though, is because you'll see that the light bulb here is doing something kind of funny. It's lighting and then becoming dim, and then lighting and becoming dim. And this does actually make perfect sense if you just pay attention to the motion of the electrons in the bulb. It becomes dim basically at the instant that the electrons are switching directions, because it's at that instant that they don't really have any speed. I always think of it as being similar to when you throw a ball up in the air. We've talked before about when the ball reaches its maximum height and is changing direction. It has a speed of 0 at that instant. Likewise, for our electrons, they're continually switching directions. And so there's going to be an instant when the direction switch takes place that they have no speed, and that there is therefore no current in the light bulb. And so for that instant that there is no current, there would be no way to have light generated in this bulb, because you need electrons to flow through the bulb to have it lit up. Now, this picture, I'm sure, might bring up some questions. You might wonder, first of all, how it's even possible for the energy to get from the voltage source to the bulb. Because our story, when we had a direct current source, was that the electrons gain energy when they pass through the voltage source, and then lose it whenever they pass through the load. And so these electrons are making loops around the circuit if we have a direct current source. But when we have an alternating current source, the electrons instead are just changing directions. And so they're not making loops around the circuit. It might not really be clear then how the energy is actually getting from this voltage source to the bulb. And here's how I think of it. I just say to myself, well, if we have an alternating current source here, that alternating current source is going to force electrons to move back and forth on this side of the circuit. But if you move an electron on this side of the circuit, you can imagine that moving that electron has an influence on the neighboring electrons, right? If I move an electron this way, say, that's going to exert a force on its neighbor, so the electron next to it is also going to move in that direction. The overall effect being that if you move electrons over here, it's also going to move electrons here. And it doesn't matter what direction the electrons actually flow through this bulb, whether it flows forwards or backwards. The requirement only is that you have electrons flowing through it in order for the electrons to encounter some resistance and for light and heat to be released. And so it's It's a little bit more counterintuitive, I would say, than direct current. But if you think about it, it's kind of okay, I think, that we have a current just switching directions, moving back and forth, and still having energy make it from the voltage source to the bulb. Now, another question that you might have thought of whenever you saw this taking place is you might have wondered, okay, so Mr. Musklo is saying that when you have a light hooked up to an alternating current source, that the light bulb is going to dim every time that the current switches directions. But you might wonder, like, how that really fits with your everyday experience, because you might not have ever noticed before that lights in your home, get dim at all. They seem to just have a constant brightness. But again, the alternating current in your home switches directions very rapidly. The frequency is 60 hertz. So this takes place so quickly that your eyes are not actually able to pick up the dimming that takes place many times a second. However, if you take a video of a particular type of light in your home and slow down the video, you can actually see that the light flickers many times a second. So I'd like to just show that to all of you. Now, I say that a particular kind of light is needed because this isn't going to work if you just use a regular incandescent bulb. If you pass an alternating current through an incandescent bulb, there will be instances where there is no current flowing through the bulb. But the thing about an incandescent bulb is that whenever you stop the current flowing through it, it doesn't just dim immediately. The way an incandescent light works is the filament gets heated and it basically gets so hot that it glows, and that's how it produces light. And so if you have an instant where there is no current flowing through it, it's not going to respond immediately and stop producing light instantly. It takes a second for an incandescent light to dim because it takes some time for the filament to actually cool down. So this isn't going to work with an incandescent bulb, but there are other types of lights that it does work. This is an LED bulb, and I took this video in my basement. This is an unfinished basement in my home, and I just use this light because it's an LED light that works for this purpose. Okay, so if I just play the video, this just taken with the slow motion setting on my phone, you can see that the light is flickering. Okay, and this is something that we just don't notice in our day-to-day experience because this is happening so rapidly that we can't see it. But if you slow it down, you can see that this light actually is flickering because of the alternating current that's feeding it. Okay, so you can try this with different lights for yourself to just see if you get this flickering effect. Some lights have components in them that prevent this flickering from taking place. So if you try it with some fluorescent bulbs, for example, it won't work. It's not going to work in the classroom. I've tried before in the classroom and it doesn't work. So, but I'm sure you could probably find some lights in your home that you can see this effect. Okay, so that's just a primer on alternating current. That's how it works. Now, another topic that I wanted to go over in this PowerPoint was electrical wiring and how your house is actually wired. Something that you might not know is that depending on what country you are in the world, outlets actually look completely different all around the world. So this is the one that we're all familiar with down here. This is the standard in Canada and the United States. And so we all know this outlet. But you can see that there are tons of other types of outlets. But what all of these outlets have in common is that they have at least two prongs. Most of them have three. in this picture. And I'm sure you've noticed in your everyday life that outlets have 3 prongs. Not all plugs that you actually plug into the outlet have 3 prongs. You might wonder why that is, and we're going to get into that. So yeah, let's talk a little bit about how your house is actually wired. All right. Now, as I mentioned earlier, this PowerPoint basically consists of a series of images. And we're getting at the part in the PowerPoint now where I'm using some images from a Khan Academy video that I found that I thought did a very good job of explaining how the electrical wiring in your house works. So I certainly will provide the link to the video as part of today's material so that you can just watch the original video as well. But for my lesson, I thought I would just use these images to help explain certain things. So just if you're wondering, I did not draw this. Okay, so what do we have going on here exactly? Well, we have a live wire that's also called the hot wire. And we have the neutral wire as well. And basically, in order for your device to be powered whenever you plug it into an outlet, there needs to be an electric potential difference between these 2 wires. And the individual that made this video is from a country where the difference is 220 volts between the live and neutral wires. Here in Canada, the difference is 120 volts. Okay, but it turns out that 220, I believe, is actually more common worldwide. But in Canada and the US, we use a smaller voltage of 120 volts. So anyways, we need a voltage difference between these 2 wires to power our device. And so the voltage difference between these 2 wires is maintained by the power station that's generating the voltage. Okay, so if I actually just go over to our simulation from earlier to just make this clear, we have an alternating current source here. And the role of this alternating current source basically is to have an electric potential difference maintained between these 2 wires. Okay, and then this is why whenever you hook up the light bulb to those 2 wires, it lights up. It's because there's an electric potential difference between the 2 wires maintained by the voltage source. Okay, so these 2 wires come from the electricity generating station, and there's an electric potential difference of 220 volts maintained between the wires. Now, a lot of people think that the electricity comes in through the live or hot wire and then returns through the neutral wire. So they think basically that the current flows from the power generating station along the live hot wire and then goes back to the generating station through the neutral wire. But if we just remind ourselves of what we just learned, we learned that these electricity generating stations are providing us with an alternating current. And so that means that the electricity, the current, is going to be switching directions going back and forth many, many times a second. So this picture of electricity going in one direction along the live hot wire and the other direction along the neutral wire is not a correct picture. That's not what happens because the current is always changing direction. But then you'd ask yourself, well, if the current is just continually changing direction here, then what really is the difference between these 2 wires? I mean, if you just have the current going back and forth, what distinction can be made between this live hot wire and the neutral one? And here's how it works. This neutral wire is maintained at a voltage that is roughly equal to the ground voltage, which we usually say is 0. Okay, so that just means simply that if you connect this neutral wire to the ground, that neutral wire is going to have the same voltage as the ground itself, so there wouldn't be any electricity flowing from the neutral wire to the ground if you did that. They'd be at the same electric potential. So this neutral wire has this voltage of 0 maintained for it. And then this live or hot wire has the high voltage of 220 volts in this image, greater than the ground voltage. So in other words, this live hot wire has a voltage of 220 volts when compared to the voltage of the ground. Now, this image is showing the case where this live hot wire has a positive voltage, which is why we have a plus sign. If this live hot wire has a positive voltage at this instant, electricity is going to flow in this direction. Okay, it's going to flow in this direction because if this one's positive and we're treating the current as a flow of positive charges, as we do with conventional current, the current is going to flow away from this positive voltage wire. And so the electricity is flowing in this direction at this instant. And then what happens is the live hot wire then has a negative voltage, so that its voltage is actually more negative than the ground. And so if that voltage is more negative than the ground, that means that our conventional current is now going to be flowing in the opposite direction. This neutral wire still has a voltage of 0. And so the whole time here, the voltage of the neutral wire is 0, and the voltage of this live or hot wire is basically switching back and forth between being positive and negative. And so it's kind of a helpful analogy that was provided in the video. They said to imagine that we have a soccer ball on a ramp that can pivot about this point here. And basically, the picture is that we have the ramp moving up and down. By moving the ramp up and down, we can move this soccer ball back and forth. So whenever we move the ramp upwards, that's going to cause the soccer ball to move to the right. When we move the ramp downwards, it's going to cause the soccer ball to move to the left. And so this end doesn't change its height above the ground at all, but this one does. It's going from being above the ground to below the ground, back and forth and back and forth. And so we have a similar situation with our live hot wire and the neutral one. The neutral wire does not change its voltage at all. It's the live hot wire whose voltage changes, being above and below the voltage of the ground wire. So that's what the difference is between the neutral wire and the live wire. Now, let's suppose, as was explained in the video, that a cat touches this neutral wire. Well, if the cat touches this neutral wire, there shouldn't be any current flowing through the cat because the voltage of the ground we're saying is 0. And the voltage of this neutral wire is also 0. Okay, it has a voltage equal to the ground. And so if the voltage is the same at these 2 points, if there's no electric potential difference between the ends of the cat, there would be no reason why an electrical current would flow through the cat. So if the cat touches this neutral wire, it's probably going to be okay. Now, I just want to make very clear before I continue that I'm not saying, therefore, that it's okay to touch the neutral wire in the outlet in your home. That neutral wire is maintained at the voltage of the ground kind of in ideal circumstances when everything's working properly, but you can't count on it. Certainly, if you actually did this, if you actually touched the neutral wire, you could end up getting a shock. So definitely don't do that. Okay, do not touch the neutral wire in your outlet at home to try this. But, ideally in a perfect world, if you did that, you wouldn't end up getting shocked because the voltage of the neutral wire is equal to the voltage of the ground. Now, what happens if our cat instead touches this live hot wire? Well, that live hot wire, remember, has its voltage changing between being positive and negative. Whether that wire has a positive or negative voltage, it's going to have a different voltage than the ground. And so that means that electricity is going to flow through the cat if there's an electric potential difference across this cat. And so our cat is going to get a shock. Okay, that's the cat getting shocked. So definitely touching this live hot wire is the more dangerous one to touch. You shouldn't touch either of them, but this live hot wire has a voltage that's very different from that of the ground. So if you touch it, you'll get a nasty shock. Okay, and now you might wonder at this point what the point is of this prong. And you might know already that this is called the grounding prong. This is where the ground wire is. Because based on everything that I've explained so far, it isn't really clear what the role would be for a third prong, because it appears that you only need 2 wires in order to power something. So for example, if I have a microwave and I plug it into an outlet, I'm hooking up the black and red wires of the microwave to the neutral and live wires that are hooked up to the outlet, that in turn come from our electricity source. And so, yeah, if I just plug in this microwave to our outlet, then we should have electricity flowing through our microwave. And indeed, that is true. If you plugged in the microwave and just completely forgot about the ground wire, you would have electricity flowing through the microwave, and things could work out fine if you did that. And just if anyone's curious, this is the symbol for a resistor, so we're just showing that our microwave is a load here, that there's some resistance. And so what is the role then of the ground wire? That's the question that I'd like to answer now. So the ground wire basically is a safety. If electricity is flowing through the ground wire, that means that something has gone wrong. And the ground wire basically makes it so that you don't get shocked, or you shouldn't get shocked if something goes wrong with the wiring in the device. So this is showing our live wire breaking apart so that the wire is exposed, and that exposed wire is now making contact with the metal casing of the microwave. Now, this is not good if this happens, because this is our live wire. It's going to have a voltage that's different from that of the ground, and if it's now connected to the casing on our microwave, it's electrically connected to it, and so that means that if someone touches that casing, they're going to get a shock. Because if someone touches the casing, then there's going to be an electric potential difference across them that's going to make current flow through them. Okay, and so we can see our cat coming along. Our cat's having a bad day. It touches the microwave casing here and ends up getting a shock because that wire is electrically connected to the casing. It's basically the same situation as before when the cat was just directly touching the wire itself. And so what's the purpose then of the ground wire? Well, it's basically a safety. The ground wire would be attached to the casing on the microwave. And as the name implies, this ground wire is actually connected to the ground. So you can see if we just follow our green wire here, it's attached to the casing of the microwave. Whenever you plug in the microwave, you're effectively connecting the casing of the microwave to the ground electrically. Okay, and the ground wires in your home actually connect to like a plate or rod that physically goes into the earth. So there is a plate or rod somewhere around your home that actually goes into the ground. And so the idea then is if this situation happened where, let's say, our live wire broke apart and started making contact with the metal casing, the electricity is not going to flow through the cat now if the cat touches the microwave casing. And you might wonder why not. It flowed through the cat here. Why is it that when we have the ground wire, it doesn't flow through the cat? And it's just simply because the ground wire has a lot less resistance in it than the cat does. And so that means, therefore, it's just much easier for the electricity to flow through the ground wire. And so it's not going to flow through the cat. Most of the electricity is going to flow through the ground wire, and our cat is safe. Okay, so that's the purpose of the ground wire. It's basically a safety mechanism so that if something goes wrong in the circuit, the electricity gets directed to the ground instead of through a person or through a device that is not meant to have a large current flow through it. All right, now I'd like to just address a question that some of you might be wondering at this point, because I'm sure that we've all seen plugs that go into outlets that do not have a grounding prong. Okay, I just included an example here of what you would plug into an outlet in order to charge your iPhone. And you can see that there's not a grounding prong here. And so you might wonder, like, okay, is that unsafe? How does this work? And the answer is no, it's not unsafe. The reason why you don't need a grounding prong for certain devices is because for an iPhone, for example, it isn't actually a potential difference of 120 volts that is being maintained across your phone itself. The reason why you have this cube whenever you plug in your iPhone to charge it is because this cube is what we call a transformer that steps down the voltage from 120 volts to a much smaller voltage that is actually used to charge your phone. Okay, and so I don't know what it is for an iPhone, but it might be like in the range of a few volts that's actually being used to charge the phone. And so this means that if something went wrong, I don't know, if some wiring went loose in your phone or something, and the live wire in your phone made contact with the case while you were touching the case, you might actually get a shock from that, but it's not going to harm you because it's not a voltage difference of 120 volts being maintained across the iPhone itself. Now, this idea that you can change the voltage, that you can step it down, as I said earlier, from 120 volts to something much smaller, that might be kind of a confusing and strange idea. We would be learning about that later in the course if we had time. Transformers are needed in order to step up or step down voltages. And there is a textbook section on transformers, so you're welcome to read it if you're interested. But I don't think we're going to have time to learn about that. That's just kind of an entirely different topic. But yeah, you can actually step up and step down voltages. So even though there is a voltage difference of 120 volts maintained across these two prongs, it isn't that same voltage that's being maintained across the iPhone. It's a much smaller voltage across the iPhone. And that's why you don't need the grounding prong. All right. Now the last slide says, what is the point of fuses and circuit breakers? And to answer that question, I'm going to pull up the third and final simulation. And then that'll be the end of the lesson. All right, so here we have a bunch of light bulbs that are hooked up in parallel to a voltage source. And you'll see that our voltage source is just a DC voltage source here, simply because that makes it easier to see what happens to the electrons when I start closing some switches. It is true that in a home, it's an alternating current source, but for the purposes of this explanation, I'm just showing it with a direct current source. So whenever you plug something into an outlet, you are hooking that device to a 120 volt potential difference. And so I'm going to do that just by closing this switch. And we're pretending here that this battery maintains 120 volts. And so I've just plugged in a device, and that device has 120 volts maintained across it. If you then plug in another device into the outlet, let's say I've hooked up an extension cord or power bar or something, and I can plug many things into this outlet, what you're doing effectively is wiring more and more devices in parallel with the outlet. And so if I hooked up another device to the outlet, that would be like closing this switch. And then if I plugged in another device, it would be like closing this switch. Okay, so there's a 120 volt difference being maintained across all of these devices, which is what you would expect just from plugging devices into an outlet. You'd have 120 volts maintained across all the devices. Okay, but you can see perhaps that as I plug in more devices to the outlet, there needs to be more of a current being outputted from the outlet in order to power all of these devices. Okay, and we've talked before in this course about how if you wire resistors in parallel, the equivalent resistance goes down. So that means that the current from the source has to increase. And so this is a potentially dangerous situation. If you just continue plugging devices into the outlet, the current is just going to keep increasing. And this can get to a point where some damage can perhaps be done. If you end up with a really large current flowing through this wire, it can cause the wire to heat up. And if the wire heats up, some insulation on it can melt, and it can cause things to heat up to the point where it could be a fire hazard as well. And so this is not good. We should have some safety checks in place to prevent the current from getting too large in this wire. And so that's the purpose of fuses and circuit breakers. Fuses and circuit breakers basically just break the circuit whenever the current flowing through them is too great. So if the current flowing through them is too large, the fuse or circuit breaker just breaks the circuit. The way a fuse works is, in a lot of cases, actually a very simple design. It's simply a piece of metal, basically, that melts if there's too large of a current going through it. So the difference between fuses and circuit breakers is that when a fuse blows, you need to replace the fuse, so they're not reusable. Circuit breakers are reusable, though. If a circuit breaks, you just flip the switch and the circuit is completed again. Now, of course, if a circuit breaks in your home, you should figure out like what the problem is because something has gone wrong. There's too large of a current somewhere in your home. But yeah, circuit breakers are reusable, fuses aren't. When they blow, you need to replace it with another fuse. Okay, and I think that's the last slide in this PowerPoint. Yeah. So that's just a crash course in alternating current and just how circuits in your home are wired. So I hope you found some of that interesting. Might have answered some questions that you've wondered before about what the grounding prong does, why lights flicker in your home, stuff like that. And so as I mentioned earlier, you can now spend some time doing the textbook questions for this section. And after completing the textbook questions, you can then start going through the concept check. And then even if you finish that, you have a culminating assignment to work on as well. So as I said, we all have work to do today. So yeah, if anyone has any questions, as always, just feel free to send me an email. But I'll just leave it there. And I hope you all have a great rest of your day and a good weekend. And I hope to get seeing all of you on Monday.